Welcome to a lesson with Dr. Powell. Let's take a look at another example of verifying that a limit statement is accurate. All right, let's do the limit as x approaches infinity of, and let's do let's make it fairly simple. Let's see. Yeah, let's do 1 over x plus 2. Okay, let's do that. All right. And we know what this limit is. This goes to 0. So 0 plus 2 would be 2. So let's verify that. Let's first write down the rigorous statement. So given, so you notice how the y value is getting close to something? So that means the y closeness is going to be an epsilon. Epsilon greater than 0. There exists, this time we just say n, such that if, there exists n such that if x is going to infinity, so x is being pushed past that position, x is greater than n, then we want the distance f of x is from 2 to be less than epsilon within the y closeness. All right. So let's take a look at this. Okay, so to do that, let's draw a picture. This is just a shift of the graph 1 over x up 2. All right, so like this. So it looks something like that. Okay, like that and like that. All right, something roughly like that, not quite exactly, but get the idea hopefully. So what we need to do is, let's see, give an epsilon. So we need an epsilon. Okay, so maybe we can draw an epsilon and kind of about the center is 2. Okay, so we're going out to a y value of 2. That's the target. And we're going up and down from the target, epsilon. Okay. Okay, so epsilon up and down. And we would like, and so you notice how we just arbitrarily draw an epsilon. I mean, it doesn't really matter which one you drew, but you do any one. Usually you do one where you can at least visualize things a little bit, because you're going to be coming up with a relationship between the x closeness and the y closeness, a dependence, functional dependency. So like n as a function of epsilon is kind of what we're looking at. So we can think, okay, so we want to figure out, you see the point of exiting, that's where we concentrate, go to the point of exiting out of the y closeness, and we mark that spot. And this spot, since x is going out to infinity, I mean, then that's just your n, okay, is that spot. So x equals n right there, signifies the x coordinate in terms of n, and then we write the y coordinate down in terms of epsilon. Y equals, we're going to 2, then we add epsilon. Then how do we relate 2 plus epsilon to n? By using the function itself. Y is equal to 1 over x plus 2. So we plug in n for x. So we have 1 over n plus 2. And for y, we plug in 2 plus epsilon. Now we find a relationship between n and epsilon by solving for n. Subtract 2 from both sides, and then take a reciprocal of both sides. N will be equal to 1 over epsilon, which makes sense because we want n to be large, and if epsilon's small, that works. So we go back to our statement, and we write, instead of there exists n, we write let n be equal to 1 over epsilon. And then instead of such that, we write then if x is greater than n, then f of x minus 2 is less than epsilon in absolute value. And we've just verified the statement. So, and of course, with the then here, we can point this way and this way for the proof. Thanks for watching.